Hi friends, welcome to the session on electromagnetics. In this video, we cover total electromagnetics syllabus in a shortest way. That is mainly the formulas to remember, and those formulas which are useful to solve problems asked in any competitive exams like GATE, TNEB, or TRB exams, right? Okay. So let us start that. We know that electromagnetics is full of formulae, but all the formulas are related and somewhat similar. If you know that similarity and relation, then it is easy to remember all the formulas. Let us start with that. Right? Okay. Right. So we know that in electromagnetics, the fields are created by charge. Charge creates field. Fine? Okay. Charge creates field. Field creates force, and that force is felt by rest of the charges. So the charge which creates field is known as source charge. The charge which is feeling that field is known as test charge. Right. So how the communication between source and test charge happens, that is what we are going to study in total electromagnetics. Fine? Okay. So first thing we study in electromagnetics is what? Coulomb's law. It gives the force between the two charges. Right? So the force between the source and test charge, let us call that. Right? So that is given by F is equal to Q1 Q2 by 4 pi epsilon naught R square R cap. Right? Where R is the distance between source charge and test charge. Let us assume. It gives the force. Okay. Then what we are going to study, the force felt by the charge, test charge. That is what electric field. So electric field is the force felt by test charge. Force per charge. But if we assume this is capital Q, this is small q, right? This is what electric field, right? So in mathematical expression, we can write as E is equal to Q by 4 pi epsilon naught R squared R cap. The unit is volt per meter, right? This is what electric field. It is a force felt by the charge. Now, from electric field, we have to take three different paths. Fine. The first path is curl. That is del cross E. Curl means del cross. So, curl of electric field is 0. That means electric field will not rotate. Electric field is irrotational. Fine. So, it indicates E is irrotational. Right? It is a point form. In differential form, we can say closed integral E dot dl is equal to 0. That means what? E is irrotational. Electric field will not rotate. We know that electric field will diverge. Say if you have positive charge, the electric field will go like this one. We never put rotational electric field. So the electric field is irrotational. And the next path we have to take is divergence of electric field. Divergence means we know it is del dot D, right? So del dot E is equal to rho V by epsilon. In free space it is epsilon naught. Similarly, D dot ds is equal to what you call Q enclosed by epsilon naught in free space. That is equal to flux. These two are known as Gauss law. Gauss law for electric field. Fine. Okay. So this is very important. So curl of electric field 0, divergence is delta D is equal to rho. So what it indicates, you see in any mathematical equation, right hand side is a cause, left hand side is effect. So charge creates field. OV is volume charge density. So charge creates field, which is diverging. So delta is diverging. So electric field is diverging field. That we know. Right? You see here, I told who is the source of field? Charge. That's what Gauss also told. Okay. So I can write this. This d dot ds can be written as E dot ds is equal to, sorry, this is E dot. If we put d dot, it will be simply epsilon naught only. Okay. Okay, fine. So E dot ds is equal to Q enclosed by epsilon naught. Right? We must know E is electric field, D is electric flux. D is equal to epsilon E. D is electric flux density. D is equal to epsilon E. R are vector quantity. Right? It is enclosed. Psi is a flux. Right? So we must know the relationship between psi and D. Psi is equal to D dot ds. I told D is flux density, right? So flux density is Coulomb per meter square. Area ds is meter square. What you get? Flux, right? You see, flux is equal to charge enclosed. That's what the unit of flux is also Coulomb. Flux density Coulomb per meter square. So the unit is Coulomb per meter square, right? Okay. So these things we must know about divergence of electric field, right? Okay, so first we understand curl, then we understand divergence. What is the only thing remaining? Gradient. So gradient of electric field. Gradient of electric field is given by, let us see how electric field is related to gradient. E is equal to minus del V. Right? So electric field is potential negative of potential gradient. Right? So that is what electric field. So that we must know about. In other words, I can say what you call E dot L. Fine. So E dot D, okay, I will say right like this. V is equal to potential is nothing but work done per charge, that is given by minus E dot D, A to B. Fine. So potential is work done per charge. It is force per charge. Electric field is force per charge. So this integral is independent of path. That we must know. Fine. Okay. This is what gradient of electric field. Okay. So next thing we must know is we studied electric field. What are the different kinds of electric field we are studying in this subject is E due to point charge. So electric field due to point charge is given by E is equal to Q by 4 pi epsilon naught R squared R cap. Fine. Electric field due to line charge. Electric field due to line charge is given by E is equal to rho L by 2 pi epsilon naught rho A rho. You see, this is dependent on path, distance. So it is distance dependent. Fine. This is also D. R is a distance. So it is also distance dependent. Next thing is electric field due to surface charge. That is given by E is equal to rho S by 2 epsilon naught N cap. Here there is no distance. So distance independent. Fine. So these are all the different charge configuration we have to. Electric field due to dipole. Right. So electric field due to dipole is given by E is equal to what you call, right? So E is equal to QD, right? Divided by 4 pi epsilon naught R cube pi into what we call 2 cos theta r cap plus sin theta theta cap. So this is what the electric field due to dipole. Okay. Next we must know is, you see, right, electric field due to charge. Electric field due to, it is monopole, only one charge. So monopole, that is dipole, E due to dipole. From this what we understand, electric field due to dipole, electric field due to monopole is depend on 1 by r square, varies with respect to 1 by r square. Electric field due to dipole varies with respect to 1 by r. Right? Okay. Next. So we know electric field is a vector quantity. It is very difficult to deal with the vector like this, right? We have to solve the mathematical will be complex. So what we need one parameter which is a scalar and which represents the electric field. That's what this potential. V is a scalar, right? We know it is very easy to deal with the scalar. So V is a scalar, E is a vector, right? So this equation converts scalar into, sorry, vector into, this converts vector, scalar into vector. Right hand side is a scalar, this is vector. This equation converts vector into scalar. So these two equations are very, very important for any exam. Fine. Okay. Now we developed a potential. Fine. So potential due to various configuration we must know. What are those configuration? Let us see. First thing is potential due to point charge. What is potential? Potential is work done per charge. Potential is a scalar quantity which is explaining whatever the things explained by what you call a vector, which is called an electric field. Potential is work done per charge, that is given by, for point charge, Q by 4 pi epsilon naught R. This is for point charge, right? So this is what potential. Next thing is potential difference. Potential difference between the 2 points, right? That is given by VA minus VB. So that is given by Q by 4 pi epsilon naught 1 by RB minus RA. Fine side, VB minus VA. This is VB minus VA. Right? Okay. So you see this is absolute potential. This is potential difference. Absolute potential is nothing but work done to move a charge from infinity to particular point to T. For that, how much work we are doing. Potential difference is nothing but moving a charge from one point to another point. Clear? So that is what potential difference. Moving a point charge, work done to move a charge from one point to another point. Here work done to move a charge from infinity to particular point. Right? Okay. So these two things we must remember. Okay. Next one is what do you call potential due to this what due to dipole. Potential due to dipole is given by V is equal to m cos theta divided by 4 pi epsilon naught r square, where m is equal to qd, which is nothing but dipole moment. Fine? Okay. So we must see, you see potential due to dipole. It is inversely proportional to r square. Potential due to point charge or monopole is inversely proportional to r. So that is very important. You see V is directly for monopole. V is directly proportional to 1 by R. For dipole, V is directly proportional to 1 by R square. Fine. So this is another thing we must know. Okay. So here also you see QD is nothing but M. That is what our dipole moment. Fine. So V is, you see here, V is directly proportional to 1 by R for monopole. For monopole, E is directly proportional to 1 by R square. For dipole, E is directly proportional to 1 by R cube. So these things we must know. They ask in all the exams, right? This is a very, very important point. Fine. Next thing we have to remember is with respect to scalar. So we studied why we are studying potential. Potential is the scalar quantity which is easy to deal with. So from scalar we have to remember two important formula. One is Poisson equation, del squared V is equal to minus rho V by epsilon naught. Second one is Laplace equation, del squared V is equal to 0. This is Poisson equation. This is Laplace equation. Right? So whenever we know about boundary condition, we can find potential by using these two. Right? So that is the thing. We have studied two important laws in electrostatics. One is Coulomb's law. Right? So Coulomb's law requires R, distance between the two charges. Gauss law requires charge symmetry or charge distribution. If these two conditions are not possible, if these two data are not available, if the distance between the two charges, if we don't know, or location of the charge, the location of the charge is not known, then Coulomb's law fails. If charge distribution is not known, Gauss law fails. Under those conditions, we can use Poisson's equation, Laplace equation. From that we can find V. From V we can find what is electric field. Right? Sorry, E is equal to minus del V. Once you find V from here, use E. E is equal to gradient of potential. Right? So in this way, potential is really helpful and make our problem very simpler. Next thing we have to remember in electrostatics is energy density. How much energy per unit volume? That is given by W is equal to 1 by 2 summation K goes to 1 to N QK 3K. Right? That is equal to 1 by 2, right? 1 by 2 epsilon E squared. Okay, let me write like this, 1 by 2 dE dV. D we know epsilon E, so 1 by 2 epsilon E square dV. Right? So this is the next thing we must remember in electrostatics. Clear? So, and another two important point we must remember is how electric field related to current. So current density J is equal to sigma E. Fine. So J is current density. You see this equation relates current density and electric field. Fine. So you see current it is ampere per meter square. Right hand side volt. So left hand side ampere, right hand side is volt. We know that V is equal to IR. Right. This implies I is equal to V by R. V 1 by R is G. So I is current, V is volt, this is conductance. You see current density, it is current at particular point. E is volt per particular point. So sigma conductivity. So we can say this is point form of Ohm's law. This is for circuit theory, this is for field theory. Find form of Ohm's law. Fine. And the last thing we have to remember, and the most thing is continuity equation. Continuity equation is given by del dot J is equal to minus dou rho V by dou T. Right? So it indicates divergence of current density. Divergence, del dot is divergence of J is equal to negative of change in rho V, volume charge density with respect to time. If you want to know the detail, please refer my playlist on AC 8451. I have explained everything in detail, right? So there you can understand. So these are all the things we learn in what you call electrostatics. That's all. So, and simplifying conclusion, what I say is, you see electrostatics. Electrostatics is nothing but study of stationary charge. Fine? Okay. Magnetostatics, study of moving charge. Fine? Okay. Next thing is electric field E, force per charge. Magnetic field, right? So next we will see, then we can, first we finish electrostatics. Right? Then we know potential work done per charge. Right? Okay. Next, what do you call charge density rho L, charge per unit length, line charge. E volt per meter, V volt. Rho L charge per coulomb per meter, charge is coulomb. Then rho S charge per area, that is coulomb per meter square. Rho V charge per volume, coulomb per meter cube. Fine. And next thing is polarization. Okay, polarization is nothing but orientation of charge. Orientation of charge. Current, movement of charge. Right? Voltage, accumulation of charge. Fine. Next, wave, oscillation of charge. Right? Okay. Next, potential work done to move a charge from infinity to particular point P. Potential difference work done to move a charge from point A to one point to another point, that is point A to point B, right? So that is what we have to know, what is potential and all, right? Okay, so in this way we can relate everything with respect to charge, right? So study of electric charge, moving charge, right? Okay, so what is electric field created? E is created by static charge. H. Magnetic field is created by moving charge. Right? So, see then what is the charge, and we have to remember all the things about charge. Fine. Next thing we have to know the important units of what you call EMF. So first electric flux. Electric flux is given by what you call Coulomb. Fine. Magnetic flux. Magnetic flux is given by Weber. Okay. So electric flux density. Okay, right here. Electric flux density is given by Coulomb per meter square. Coulomb per meter square. Fine. Okay. Next, magnetic flux density. We know it is Weber per meter square or Tesla. Okay. Magnetic charge. We know electric charge is Coulomb, magnetic charge is ampere meter. We have close loop. So electric charge Coulomb. Fine. Okay, then scalar magnetic potential, it is ampere. Scalar electric potential, volt. Yes or no? Yes. Then vector magnetic potential is given by Weber per meter. Okay. Then what do you call current density? Current density. Current density means area. So current is ampere, density is ampere per meter square. Right? Electric dipole moment. Electric dipole moment, that is given by QD. Q is Coulomb and D is distance meter. So that is what electric dipole moment. Magnetic dipole moment ampere meter square. Right? Okay. Electric current density J. Fine. Next, torque. Force into distance, Newton meter. Right? So, magnetic current density. Magnetic current density. That is given by volt per meter square or Weber by meter square second. Right? So those things we must know. And another thing we must remember is Stokes Theorem. Fine. Stokes Theorem relates line and surface integral del cross A dot ds is equal to A dot dl. This is surface, this is line. Right? So if you know what is the detail about Stokes theorem and all, please refer my video on EC8451 series. Right? I have covered in detail. It is very easy to remember why line and surface are related. Everything I explained. And for divergence theorem, it is divergence delta D dV. It relates volume and surface D dot ds. Fine. So it is volume. It is surface. Then I think we are using only these two theorems, Wien's theorem and all, we never use. Right? So these are all the things we must know about what you call electrostatics. Right? Next we study about magnetostatics. Now we start about magnetostatics. Right? So it is what is magnetostatics? Study of moving charge. So first thing we have to know about in magnetostatics is what you call Biot-Savart law. Biot-Savart law, right? Which is given by, it gives the relationship dH is equal to IDL cross R vector divided by 4 pi R square. It states that a current element creates magnetic field, right? We know electric field is created by stationary charge. E is equal to, right? Sorry, del dot E is equal to rho V by epsilon. Static charge creates electric field. Ideal is nothing but current element. So ideal current element. Right? So in current element we have moving charge. So moving charge creates magnetic field, right? So for line current, H is equal to closed integral ideal cross R vector divided by 4 pi R square, right? This is line current. Fine, okay. So you see, if you integrate, you will get this. This is dH. If you integrate, you will get H. Why it is closed? Because current will flow through the closed path only. So in magnetic field, always we have to use closed integral. Because magnetic field is created by moving charge. So H due to surface current is given by S K ds, right? K ds cross R vector divided by 4 pi R square. This is surface, it is magnetic field due to surface current. K ds is surface current, right? Next, dl is vector. H due to volume current V, J dV star cross R vector divided by 4 pi R squared volume current, right? So this is in similar with the electric field, right? We know it is similar to Coulomb's law. This is Biot-Savart law, Coulomb's law. We know F is equal to Q1 Q2 by 4 by epsilon naught R squared R cap. You see this is also R. R is the distance between the source and the field. So both are electric field we know Q by 4 pi epsilon naught R squared R cap. So E is inversely square law 1 by R squared. Similarly H is also inverse square law. And Biot-Savart law and Ampere circuit law are for magnetic field. The equivalent version is Coulomb's law and Gauss law in electric field. Right, everything I explained in detail in my playlist EC8451 Electromagnetics. So there, if you want detailed analysis which is useful for your GATE exam also, so we can learn everything in detail in that playlist. Okay, now similar to electric field, we have magnetic field. It has three paths. What are those three paths? First we see divergence, right? So when you take a divergence of magnetic field, del dot B is equal to 0. Fine. And B dot ds, the equivalent version is B dot ds is equal to 0. We know B is equal to mu H. H is magnetic field, it is magnetic flux density B. So divergence of magnetic field is 0. Dot means divergence, we know, right? Okay, del dot divergence. Okay, next, what about curl? Curl of if you go in this way, we will get curl. We know del cross H is equal to J. H dot dl is equal to I enclosed. This is known as Ampere circuit law, right? Which is equivalent to Gauss law of electric field. So you see del cross curl of magnetic field is current density. That is again it is telling Current introduce magnetic field. In any equation, right hand side is cause, left hand side is effect. So current introduces magnetic field. Okay. So next, what are the things we have to remember? H due to what you call H due to infinite line charge. So H due to infinite line charge, infinite current carrying element is I by 2 pi rho A phi. It is due to infinite current carrying element. Right? You see the magnetic field pi is rotated because pi varies from 0 to 2 pi. It is creating rotational magnetic field. Right? So that is very, very important. Okay, then H due to infinite current sheet, that is given by 1 by 2 K vector slash n cap. Right? You see here H is independent of distance, independent of the distance from the sheet. Wherever you find magnetic field due to sheet, that it is independent of the distance. That is another thing we have to remember. Okay. Next. Okay. Gradient. Fine. Like gradient, we have to go this side. Fine. Here what we learn. This is telling we have to create potential. Right? So you see H vector is equal to minus del V, magnetic potential. E is equal to minus del V, H is equal to minus del V. Fine, this relates scalar, this is vector. Okay, then we know del squared V is 0 for electric potential. It is magnetic potential, it is Laplace for magnetic field. Laplace equation for magnetic field H. For electric field, del squared V is equal to 0. Similarly, we have Poisson's equation for magnetic field, del squared A is equal to minus mu naught J. A is vector magnetic potential. Fine? Okay. Vm is scalar magnetic potential. Then another thing we have to know, fine, this is the thing we have to remember. Okay, so this relates potential gradient, right? Gradient of magnetic field in what way it is related to gradient? Magnetic field is negative of magnetic potential gradient. Okay, next, what are the things we have to remember? Okay, we have to remember about potential of vector magnetic field. So B is equal to del cross A, right? It is magnetic flux density, right? This is vector magnetic potential. Fine. Why we don't have vector magnetic potential? Everything I explained in EC 8451 series. Please refer. Okay, so this is very, very important relation. From this relation, they may ask any questions. Okay, next, what we have to know? A. We have to represent A in different way. The vector magnetic potential is given by A is equal to mu naught IDL divided by 4 pi R. You see, in electric field also potential is directly inversely proportional to R. In magnetic field also potential is inversely proportional to R. It is due to line current element. A is equal to mu naught KdS divided by 4 pi R. It is due to surface current element. Similarly, A is equal to KdS, sorry, K mu naught J, right? Mu naught J dV by 4 pi R. This is for volume current element. Fine? Okay. Similarly, we know electric flux is given by d dot ds, right? Magnetic flux is given by b dot ds, right? So this is Coulomb per meter square, electric flux density, this magnetic flux density, Weber per meter square, Coulomb, it is Weber. Fine. So we remember another one, J dot ds is equal to I. You see everything, right? Ampere per meter square into meter square ampere. Fine. So similarly, we have one more equation with ds that we should remember in pointing vector, right? So pointing vector is power flow per meter square. S is pointing vector, power per meter square into meter square. That is equal to P, right? So all those ds formula we must know. This is very simple, right? Electromagnetic is full of relations, right? It is easy to remember all the relations. Okay. Next, what we have to learn, we should know force equation, Lorentz force equation, right? We know electric force due to electric field is QE, force due to magnetic field is given by QV cross B. Force due to electric field QE, force due to magnetic field is QV cross B. Total force experienced by a charge is QE plus V cross B. This is what we know as Lorentz force equation. Fine? This is very important formula. Okay, so then force due to line is given by IDL cross B. Right? In surface, force is given by closed, everywhere it is closed. KDS cross B, fine, L line, DS surface, SC, F is equal to JDV cross B, this for volume. Fine? Okay. Next, force between current carrying element. Force between two current carrying elements is given by, it is force per length, which is equal to mu naught I1 I2 divided by 2 pi d. D is the distance between the elements, right? So this is another important point. Then we have to know torque. Total torque is given by BIA, flux density, current, area, right? So if you have n loop, if the loop contains n turns, NBIA. In vector, tau is equal to R cross F. This is torque. Fine. Dipole moment, M is equal to, I told already, ampere meter. So I is current, fine. Okay. So this word we should remember in magnetic field. Right. So gradient, divergence, curl, everything is explained. So you see, simple logic to remember all the formulas of magnetostatics, right? So very simple, please understand it, right? Next we go for waves. Next we learn about electromagnetic waves, right? So the fundamental for electromagnetic waves, we know it is Maxwell's equations. So Maxwell's equation, right? So what is the first Maxwell's equation? It is Gauss law for E field, electric field, that is given by d dot ds is equal to q enclosed, right? Similarly, in point form, it is delta d is equal to rho v. This is integral form. This is point form. Next, what is Gauss law for magnetic field? Gauss law for H, that is given by b dot ds is equal to 0. Similarly, del dot b is equal to 0. Then Faraday's law, That is given by E dot dl is equal to minus d phi by dt, that is equal to minus d by dt bds, closed integral E dot dl. Right here, del cross E is equal to, okay, write properly, del cross E is equal to minus dou B by dou T. Then modified Ampere circuital law, that is given by H dot dl is equal to Jc, that is sigma E plus Jd epsilon 2E by dou T dot ds. That we can write as Jc plus Jd dot ds. Similarly here, del cross H is equal to sigma E plus epsilon dou E by dou T, or del cross H is equal to Jc plus Jd, right? Where Jc is equal to sigma E, Jd is equal to epsilon dou E by dou T, that is dou D by dou T. Right? Okay, here you see that's the most beautiful equation. Right, from here we will understand electric field is created by charge. Q is creating electric field. D is nothing but epsilon E. So electric field creates charge. Charge creates electric field. Charge creates electric field. Right? This indicates no magnetic monopole. Right? The explanation I have given in my video, please see. No magnetic monopole. Fine. And you see, Faraday's law states that change in magnetic field, d by dt, change in magnetic field create electric field. Here you see, change in magnetic field, B, dou V by dou T. The time varying magnetic field. Magnetic field varies with respect to time. Time varying magnetic field will create change in electric field, spatially varying. Del is a spatial operator. So it is spatially varying E, it is time varying B. So time varying magnetic field will create spatially varying electric field. That is, change in magnetic field creates change in electric field. Here, modified Ampere circuital law or Maxwell's law. Ampere-Maxwell's law. This indicates, you see, change in electric field. From here you can see dou E by dou T. Change in time varying electric field creates spatially varying magnetic field. So both are opposite to each other. So Faraday is the first person who brought the term time, right? Before that, there is no time involved in the electric field. You see, first time we can see time, right? So we have to credit Faraday for research on time varying field. Fine. So Ampere circuital law. Next we have to see Ampere circuital law. Ampere circuital law is del cross H is equal to J only up to this. Fine. Maxwell introduced this term. So this is J. So Jc is conduction current density. Conduction current density. This is Jd, displacement current density. The biggest contribution of Maxwell to the EMF is displacement current density, or biggest contribution of Maxwell to the whole world, displacement current density, Jd. You see conduction current and displacement current. You see displacement current is due to field, right? So conduction current is due to charge. So Jc due to charge, that is very important point. Jd, displacement current, is due to field, electric field. That is very, very important, right? Don't forget this question, they have asked many times. Fine. So that thing we have to remember. Okay. Next we have to study EMF is pointing area. Pointing theorem. Pointing theorem is telling that this pointing theorem states that S is equal to E cross H. Right? E is volt per meter, H is ampere per meter. So it is volt into ampere, V into I, power per meter square. So it indicates power flow. right? If E flows in X direction, H flows in Y direction, then wave should flow in Z direction only. How it has come? Please refer my video on EMF, right? Okay, similarly, next thing we have to know this is what Poynting vector. So I think it is enough. And the energy density of the wave, energy density of the wave is given by small we 1 by 2 epsilon e square, right? So these things we have to remember. Then average Poynting vector, time average Poynting vector. From this they ask so many questions in GATE exam. Time average Poynting vector, P average is equal to 1 by 2 real part of E cross H star, right? Or P average is equal to 1 by 2 E squared by eta, where eta is equal to E by H. Fine. So this is very, very important thing we have to know. Next parameter, next thing we have to remember is wave boundary conditions. Boundary condition, very, very important, right? Okay. So in boundary condition, what we know for electrostatics, we know tangential component of electric field is equal to same, right? Similarly, dN1 minus dN2 is rho s. This implies epsilon 1 En1, epsilon 2 En2 is rho s. Tangential component is equal, normal component is not equal. So tangential component of electric field at the boundary is same. Et1 is equal to Et2, but normal component of electric field is not same. dN1 minus dN2. This is for electric field. Similarly, for magnetic field, HT1 minus HT2 is equal to Js. Because electric field is created by charge, magnetic field is created by current. So Bn1 normal component is equal. Bn1 is equal to B2. Fine. And Jn1 is equal to Jn2. Right. So Jt1 is equal to sigma 1 by sigma 2 into Jt2. This is what for magnetic field H. Tangential component of magnetic field equal, but tangential component of magnetic field is not equal. Similarly, normal component here equal. Here normal component is equal. Fine in magnetic field. Okay, next what we have to know, electromagnetic boundary condition. This is what electromagnetic boundary condition. Next we have to remember important point is for dielectric, for very good dielectric, conduction current is zero. Sorry, JC is conduction current, right? For very good dielectric, JC is equal to 0, right? Okay. For conductor, JD is equal to 0. That means current in dielectric is due to field, displacement current. Current in dielectric is due to charge. That's what it indicates. Okay, right. We know time varying, potential for electric field and potential for magnetic field. For time varying field, right, E is given by minus del V minus A. Very, very important. Right? Okay, this is what we have to remember. Then wave equation for conducting medium. Wave equation for conducting medium is given by del square E is equal to mu epsilon dou squared E by dou T square plus mu sigma dou squared E by dou T square. Sorry, dou E by dou T. Right? So this is what this one. Next, for magnetic field, wave equation is mu epsilon dou squared H by dou T squared plus mu sigma dou h by dou t. Similarly for free space, sigma 0. So del squared E is equal to mu epsilon dou squared E by dou t squared. Del squared H is equal to mu epsilon dou squared H by dou t square. In free space sigma 0, so this term will be 0. Right? Okay. This we must know. Fine. And I think that's all about this. Right? So I hope this will be really helpful for you. If you have any doubt, please refer my playlist EC8451 Electromagnetics. There I have explained everything in detail. Thank you. Hi friends, in this video we see the gist of a transmission line in an hour, right? So I try to cover most of the concepts and important formulas that can be used for competitive exams. First we understand what is transmission line, right? So transmission line I write like this. Actually transmission line is a device which is used to transport EM energy, electromagnetic energy at microwave frequency from one point to another point, in a system without radiation of energy, taking place. Fine. So this is the definition of right. So transmission line. So transmission line is a device a system of device, right, used to transport electromagnetic energy at microwave frequency. That is very important. So it transports electromagnetic energy at microwave frequency from one point to another point without loss of or radiation of energy taking place. The first thing we must know in transmission line is the equivalent circuit of transmission line, right? That is given by like this. Fine. So it has RL in series and GC in parallel, right? So it goes like that. Fine. So this is resistor, inductor, conductor, and capacitance. Fine. Okay. Now we see what is the impedance of the circuit. Z is equal to R plus J omega L. Right? And admittance Y is equal to G plus J omega C. Okay. So these are all two important equations. From this we get two important points, that is primary constant. Primary constants are resistor, inductor, conductor, and capacitor. Then there is secondary constant. Secondary constants. Okay, what are those? They are Z0 and gamma. Where Z0 is what you call characteristic impedance. Fine. And gamma is propagation constant. Okay. Fine. Then next thing we must understand is what is the relationship between this constant, primary constant, and secondary constant. Right? For distortion line, a line with distortion, the relation is given as gamma. Propagation constant is root of z into y. right? So what is that? R plus j omega L. Why is G plus j omega C? So gamma can bear it as R plus j omega L, G plus j omega C. Fine? Okay. Next thing we have to remember is Z naught. Z naught is Z by Y. So Z we know R plus j omega L, Y is G plus j omega C. This is a very important equation. Now you see, if you multiply these two, Z naught into gamma, Z naught into gamma, if you multiply G omega C will be cancelled. What we get is R plus j omega L. Right? If you divide gamma by Z omega, Z naught, what will happen? Gamma, this one, R plus j omega will be cancelled. It will be G plus j omega C. You see, this is giving the relationship between the primary constant and the secondary constant. These R plus R, L, G, C are primary constant, Z naught and gamma are secondary constant. So this equation relates primary constant and the secondary constant. Next, we have to see what is the voltage and current at any point on a transmission line. So V and I at any point on a transmission line. That is given by V is equal to V naught cos H gamma X plus IR Z naught sin H gamma X. Similarly, I is equal to IR cos H gamma X plus VR by Z naught sin H gamma X. Fine. So Z naught we know, IR is a current, gamma propagation constant. It is a point at any point. Any point is X. Fine. So this is the thing we must remember. Okay. And this is the voltage and the current at any point on a transmission line. Okay. So another thing we have to know is gamma propagation constant is related to current and voltage like this. Gamma is equal to 20 log Vs by Vr. Otherwise 20 log Is by Ir. Fine? Okay. Now we come to the important part of this session, the lossless line and distortion. So when a line is called a lossless line, when a line is called a distortion. Right? So this thing is very important. And there are a lot of questions asked from this area. Let us see that. Yeah, lossless line has characteristics like this. One is R0, R is equal to G is equal to 0. That is, both resistance and conductance are 0. Second, conductivity infinity. Right? So conduction is infinity. Conductivity is infinity. Then third one is gamma is equal to J beta. That is, alpha is equal to 0. So I have to tell something here. Right? We know gamma is equal to propagation constant. Gamma is given by alpha plus J beta. Alpha is attenuation constant. Right? Beta is phase constant. Fine? Okay, so this is another important equation you must remember. So what happens here is, for lossless line, attenuation is 0. That's why it is called lossless. See, that is very important. Right? For lossless line, attenuation, it has no loss. No loss means attenuation is 0. If attenuation is 0, then propagation constant is purely a function of phase constant. So it is not that is, it is because of attenuation is 0. Okay, fine. Then fourth characteristics of lossless line is beta is equal to omega root LC. Then Fifth one, Vp, that is phase velocity. V is velocity, P is phase. We know Vp is equal to omega by beta, that we studied in EMF itself. So that is 1 by root LC. Similarly, the characteristics impedance is Z0 is equal to L root of L by C. Right? So these are all the characteristics of lossless line. A line with these characteristics are called lossless line. Next we study about distortionless line. So for distortionless line, this line is the condition is R by L is equal to G by C. This question they have asked in different exams. So this condition is very important. Then another thing here we know alpha 0. Here alpha is independent of frequency in distortionless line. Alpha is independent of frequency and beta is dependent from frequency. Beta is dependent on function of f. Here alpha 0. Fine. So this is another important point to be noted. And here alpha is not equal to 0. Alpha is equal to R into G. Right. So that is given this one. And beta is equal to, as usual, omega root LC. Vp, we will get the same answer, 1 by root LC. And Z0 is also, what do you call, root of L by C. So you see root of L by C from here, this implies this L by C is equal to R by G. So L by C, that is equal to root of R by G. So this question they have asked one time, right? Instead of giving Z0 is equal to root of L by C, they have given Z0 is equal to R by G for distortionless line in the option. So this is another important point we must know. Okay. Then the main conversion formula we use in transmission line is what you call ampere into decibel. So we must know 1 ampere is equal to 8.686 dB, right? And 1 dB is equal to 0.115 ampere. Right, so this is another important definition we have to know. Right, 1 ampere is this one, 8.686 dB. Fine. Okay, next thing we have to see is input impedance of different load. Very important area. So input impedance of different load. Right, we have to remember these equations because a lot of questions are based on this one way. Okay, right. Let us see this. The type of a line. Sorry. Type of line. Here, what is input impedance? Right. So first one, lossy line. Lossy line, for lossy line input impedance is Z0, ZL plus Z0 tan H gamma L divided by Z0 plus ZL tan H gamma L. This is the input impedance of lossy line, right? Then input impedance of a lossless line. What is lossless line? Alpha 0. And alpha 0, what is Z0? Z0 is equal to ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. Fine. So you substitute gamma is equal to alpha plus J beta. With alpha 0, this implies gamma is equal to J beta. Why alpha 0? Because it is a lossless line. So if you substitute gamma is equal to J beta, you will get this formula. So this is the input impedance of lossy and lossless line. Okay, next. Input impedance of lossy short circuit load. That is, load is short. So load impedance is 0. So at that time, what is input impedance is Z0 tan H gamma L. So the impedance is known as short circuit impedance because load is short. Then lossy open circuit load. Open circuit load means our load is open, that is impedance is infinity. So that is given by Z0 cot H gamma L. So I can write as ZOC. So if you have any doubt how to remember, you see open means cot, OO. Short means tan, right? Oh, so O to O you remember, short we can write as tan. Then for matched load, that is ZL is equal to Z0, it is matched condition. Fine. For matched condition, input impedance is Z0. Clear? So this is for lossy. For lossless load, lossless short circuit line, that is L is equal to 0. Fine. So ZSC is given by JZ0 and beta L. This is for lossless. For open circuit, ZL is equal to infinity. ZOC is equal to minus JZ0 cot beta L. Fine. Then for matched load, ZL is equal to Z0. That is, load impedance must be equal to characteristics impedance. Zi is equal to Z0 also. Fine. Here, short circuit behaves like a parallel response. That is another question they are asking regularly. So, short circuit behaves like a parallel response, whereas open circuit behaves like a series resonance. Fine. So, these 6 formulas are very important one, right? Then we will see some other important definition. What is return loss? Return loss is given by, first I read the definition. It is a difference between return loss, difference between forward and reflected power, right? So whether return loss should be high or low, return loss must be very high. Why? Because you see RL, return loss is equal to difference between forward power minus reflected power. So FP minus RP, reflected power. So for a very good transmission line, reflected power should be very less. So if RP is less, then the difference will be very high. So this implicates RP must be low. This implies RL must be very high. Right? So that is the first thing we must remember. So the formula to find the return loss is given by RL is equal to minus 20 log of mod gamma. Where gamma is a reflection coefficient, I will deal it soon. Fine? Okay. So next thing we have to see is reflection factor. Reflection factor. That is K is given by 2 into root of Z1 into Z2 divided by Z1 plus Z2. Right? Okay, this is called reflection factor. So what is the definition for reflection factor? It is a change in load current change in load current due to reflection. Due to reflection. Where the reflection will take place? Reflection at the mismatched junction. Right? So it is a change in load current due to reflection at the mismatched junction. Okay. Then reflection loss. Reflection loss is given by 20 log of root mod Z1 plus Z2 divided by 2 into root of Z1 into Z2. Right? So this is called reflection loss. Okay. Now we come to the important point that is called reflection coefficient. Reflection coefficient. Right? That is given by the symbol gamma. Right? So gamma is a ratio of how much of power incident to how much of power reflected. So out of how much power incident, how much power is reflected. Right? So that is given by reflection coefficient. Right? So this is the incident power. Out of the incident power, how much is reflected? That is given by reflection coefficient. Right, in terms of impedance, it is given by ZL minus Z0 divided by ZL plus Z0. ZL is load impedance, Z0 is characteristics impedance. Load impedance, this is characteristics impedance. Fine, okay. So you see gamma is equal to 1 for open circuit. Open circuit means what you call load is having a infinite impedance, right? So what will happen? Open circuit means ZL is equal to infinity. So gamma ZL I take outside 1 minus Z0 by ZL. Yeah, ZL 1 plus Z0 by ZL. So this cancel. ZL is infinity, so 1 by infinity is 0. This is Z0 by infinity is 0, so it is 1. Similarly, minus 1 for short circuit. Short circuit means ZL 0. So 0 by this is 0, this is 0. Minus Z0 plus Z0, so minus 1. So gamma is equal to 0 for matched load. Matched load means ZL is equal to Z0. Open circuit, ZL infinity. Short circuit, ZL 0. When ZL is equal to Z0, 0. ZL is equal to Z0 means gamma will become 0. So matched load means all power will be transferred to the load. So what will happen to reflected power? Reflected power is 0. So gamma is 0. Fine? Okay. Next one is we have to study about voltage standing wave ratio. Voltage standing wave ratio, which is having a symbol S. So S is given by V max by V minimum, that is voltage max to the voltage minimum, or current max to the current minimum. Clear? So I can write S in terms of gamma as this very important relation. A lot of questions will be asked from this area. 1 plus gamma divided by 1 modulus. This is equal, this implies gamma is equal to S minus 1 divided by S plus 1. Otherwise, I can write gamma as V max minus V minimum divided by V max plus V minimum. Here you substitute S is equal to V max by V minimum, we will get this formula. So another thing we must know is gamma ranges from 0 to 1, right? So reflection, you know, reflection gamma is given by PR divided by PI. So out of incident power, the reflected power will be at most all the incident power will be reflected. So PR is equal to PI means it will be 1. When PR is equal to PI, that is all the incident power are reflected. Otherwise, no power will be reflected. That means matched. So it is 0 by PI, 0. So the minimum range is 0, maximum range is 1. This is the range of gamma reflection coefficient. If gamma varies from 0 to 1, then S varies from 1 to infinity. Why? Because S is equal to 1 plus gamma divided by 1 minus gamma. When gamma 0, S is equal to 1 for gamma 0. S is equal to infinity for gamma 1. When you substitute gamma 1 here, then it will become infinity. So S ranges from 1 to infinity. These two are very, very important point. Fine? Okay. And the next thing we have to remember is to suffer a 5-degree phase shift. To suffer a 5-degree phase shift in a distortionless line, the wave has to travel. The wave has to travel beta L distance, that is equal to 5 degree. This implies L is equal to 5 degree by beta, right? So L is a length. So beta L is electrical path. I can say it is a length of electrical path. We know beta is a phase constant. And phase velocity Vp is given by phase velocity Vp is given by, we must know, omega by beta, that is equal to 1 by root of mu epsilon. This is another thing we have to know. The next thing we should remember is, what do you think, when line is terminated by purely resistive load, what happens? VSWR is equal to RL by R naught if RL is greater than R naught. Similarly, VSWR is equal to R naught by RL if R naught is greater than R. Right? Purely resistive load means Z is equal to R. So that is what we have to know. So Z naught is equal to, RL is equal to ZL. Right? Purely resistive load, Z is equal to R. See, for if RL is greater than R naught, what is the VSWR of purely resistive load? RL by R naught. Because we know S must be greater than, yes or no? So S must be greater than 1. So RL is greater than R naught. So RL must come into the numerator. So that is a very, very good. Here R naught is greater than RL. So R naught should come to the numerator because S must be greater than 1. This is another thing we should remember. Okay. Then we will see what is the impedance distribution of open circuit and short circuit line. So input impedance distribution of open circuit and short circuit in dissipation machine. Fine. So what we have to do? First we must know length of line. Right? Then we must know equivalent circuit element. Fine. we see whether it is open circuit or short circuit. So when the length of the line varies less than lambda by 4, when length of the line is less than lambda by 4, open circuit behaves like a capacitor and short circuit behaves like a inductor. Right? And another thing is, we know for a dissipationless line, what is it then? Zn is equal to minus jz0 cot beta L, because open circuit, open contact. Here jz0 tan beta L. What we are going to find? Input impedance. Okay. Then open circuit acts as series resonance. Short circuit acts as tank circuit. Right? So this is another thing we have to remember. Fine. And when L is equal to lambda by 4, when L is equal to lambda by 4, open circuit acts as series resonance, short circuit acts as tank circuit. Fine. So this is for L is less than lambda by 4. Next, when the length of the line lies between lambda by 4 to lambda by 2, open circuit acts as an inductor, short circuit acts as a capacitor. Short circuit line acts as a capacitor. Okay. So here what is our impedance? Again minus jz0 cot beta L, because open circuit. Impedance here is jz0 tan beta L. Here when L is equal to lambda by 2, what happens? Open circuit acts as a tank circuit and the short circuit acts as a series resonance circuit. Fine? Okay. In graphical format, how can I write? This can be written as, I can draw. Right? When L varies from 0 to lambda by 4, lambda by 2, 3 lambda by 4, lambda L XOC by R naught. Right? This is open circuit. So open circuit. 0 to lambda by 4, you see when L is varying, when L is 0 to lambda by 4, it's a capacitor. So 0 to lambda by 4, we draw like this. It is going like this. This is positive impedance, so it is positive. This is negative. So positive means L, negative means C. We know the reactance. So what will happen? It is going like this. So it is 0 to lambda by 4, it is capacitor. Lambda by 4 to lambda by 2, it is inductor. Here, similarly, here you can see. Fine. Okay. From lambda by 4, again the same thing will repeat. So here it is capacitor, it acts as a capacitor. Here it acts as an inductor. So we can see that from 0 to lambda by 4, open circuit acts as a capacitor. Lambda by 4 to lambda by 2, it acts as an inductor. So 0 to lambda by 4, capacitor, lambda by 4 to lambda by 2, inductor. The same thing will repeat for every lambda by 2. So again it will go like this. Fine? Okay. So you can draw like this. So from this diagram also you can understand what is the nature of impedance. Okay. You see x-axis is like how impedance behaves. Okay. How open circuit line and short circuit line behaves. We will see next for short circuit line. Fine. So this is the length of the line. Short circuit. So reactance XSC by R positive, negative. This is talking about L, this is talking about C. right? From 0 to lambda by 4, lambda by 4 to lambda by 2, 3 lambda by 4 plus lambda. 0 to lambda by 4, short circuit behaves, behaves 0 to lambda by 4, short circuit behaves like inductor. Lambda by 4 to lambda by 2, it is behaving as a capacitor. So 0 to lambda by 4, it behaves as an inductor. Inductor means positive side, positive reactance. So it is going like this. Lambda by 4 to lambda by 2, capacitor. Right? It is behaving like capacitor. So this is L, this is C. Again, after lambda by 2, the process will repeat for next half cycle. So it will become like this. Fine. So this is what we must write off again. It is going like this. Fine. So it will go like this. Right. This is the way impedance is distributed along the length of the line. Right. Okay. Next, we learn about voltage and current distribution in dissipationless line. So V and I distribution in dissipationless line. Right. So the voltage of the dissipation line is given. Dissipationless line is given by VL cos beta L plus J IL R naught sin beta L. Similarly, I is equal to IL cos beta L plus J VL by R naught sin beta L. Okay. So this is very important thing we must know. Now we see how we can find all these values for open circuit and short circuit load for dissipationless line. So for open circuit load, IL is equal to 0 because open circuit means current is 0. For that, V is given by VL cos beta L. Because IL 0, so this term will be 0, so V is equal to. You substitute everything here because what we are going to find is what is voltage and current in open circuit load. Right? So V general equation is V is equal to this one and I is equal to this one. For open circuit load, IL 0 means V is equal to this one. Similarly, I is equal to IL0, so it will be JVL by R naught sin beta L. Okay, fine. Next thing we must know is, here you see, fine. It is an open circuit load, so at load current will be 0. This is load. Since it is a load, we know it is open circuit load. At load current will be 0. Let us assume this is the length. At load current will be 0, and the diagram for current will be appearing like this. This one, and this. This is for I. Right? So at open circuit, voltage will be maximum. So see the maximum will be like this. Fine. So it will be like this. It is going like this. Fine. So again it will be like this. From here like this. Again it goes like this. From here like this. Fine. Okay. So what happens? This is for voltage wave. See, at open circuit voltage is maximum. So V max current is 0, I 0, right? So when voltage maximum occurs after lambda by 2. So that is the first thing we must know. The adjacent distance between the two maximum or minimum is lambda by 2. So this is maximum, this is maximum, this is minimum, this is minimum current. So it is lambda by 2. So next to maximum occurs here. So it is lambda. So that we have to remember. Okay. So I noted from here the distance. So you see, so it must be lambda by 4. Right? So the distance between the two maxima, that is very, very important. Distance between Vmax, two voltage maxima or minima. Two minima is lambda by 2. Right? Distance between Vmax and V minimum. Similarly, Imax or I minimum is lambda by 4. So distance between maxima and minima is lambda by 4. Distance between two maxima. Here you see maxima, this is maxima, voltage maxima. This is voltage maxima. So distance is lambda by 2. Here maximum, next to maximum occurs here lambda. So distance between two max or two minimum. You see current minimum here and here. Another current minimum occurs at here, right? So lambda by 2. So distance between two minima is lambda by 2. Distance between maximum and minima. You see here V max, V minimum, lambda by 4. I minimum, I max, lambda by 4. Okay, that is very, very important. Then it is a first, second point. Let us assume this is the first point. Oh, sorry. What is the voltage of the open circuit load in dissipation S9? Current and voltage and current waveform. Okay, suppose if fourth one is if L is equal to lambda by 4 or at L is equal to lambda by 4, VOC becomes 0, IOC becomes JVL by R naught. This implies power is V by I, V into I. So at L is equal to lambda by 4, you see at L is equal to lambda by 4, you substitute beta is equal to 2 pi by lambda, this lambda L is equal to lambda by 4, pi by 2, cos pi by 2, 0. So what is happening? V is equal to 0. Sin pi by 2, here if you substitute, it will become sin pi by 2, 1. So at L is equal to lambda by 4, V 0 and IOC is JVL by R. Because we are talking about open circuit line, so I say VOC, IOC. So when you multiply power, V into I, 0. Similarly, we have to deal for short circuit line. Fine, follow the same procedure. Short circuit load, that is IL is maximum or VL is 0. Means short circuit voltage is 0. So what happens if you substitute VL 0 here, it will become V is equal to JIL. V is equal to JIL R naught sin beta L. I is equal to IL V0. I is equal to V0, VL is 0. So this term will be 0, only this term will be there, IL cos beta L. Similarly, at load, what happens? This is at load. VL0, because we know short circuit load, so V0, short circuit means current is maximum, right? So here at load, you see voltage maximum, current is 0. Fine, okay. Now we draw the diagram. How to draw? Follow the same procedure. This is load. This is length of the line, right? So you can see V at load V0, right? So V0 means it will start from here and it goes like this. This is V at load 0. Again it will be 0 at lambda by 2. Again it is 0 at lambda. Similarly, at load current is maximum. So it will be I max is 0. After lambda by 2, it will reach max. Fine. Okay. So it will be going like this. Again, you see, it is maximum, maximum, lambda by 2. Maximum, maximum, lambda by 2 distance. Minimum, maximum, lambda by 4. This is 3 lambda by 4. Okay, this is the way we have to know. Next thing we have to understand is, similarly we can find it for what will happen to the V and I at lambda by 4. Next, what we have to do, what will happen to the matched load? If the load is matched load means ZL is equal to Z naught, right? So for matched load, it is matched, so V and I will be like this. This is as usual V, this is length, here it is height. For matched load, it will be like that, right? So that means constant voltage magnitude. Fine. This is what, so V is given as V is equal to VL e power j beta L, I is equal to IL e power j beta L. Fine. Okay. So if you take magnitude, mod V becomes VL because mod e power j is 1. So this is what the diagram for matched load. Okay. At L is equal to lambda by 4. Here you see similarly, I forgot to mention here, at L is equal to lambda by 4, what will happen? At L is equal to lambda by 4, what is V? What is I? So at L is equal to lambda by 4, sin beta by 2, so JIL Z, sin pi by 2, so JIL R naught, right? So JIL R naught, similarly I is equal to 0. That is proved, right? At lambda by 4, you see I0. I0, right? Okay. Next, what we have to learn is, so far we studied what is voltage and current distribution and dissipation lesson, right? So these are all the conditions for dissipation, voltage and current distribution and dissipation line with open circuit load and short circuit load. Now we will see for resistive load. So we studied for open circuit load and short circuit load. Now we go for resistive load. Fine. If the load is resistive, RL is greater than R. That is RL, RO must be less than RL, both must be less than infinity. If it is infinity, it will become an open circuit load. So that is what we must know. So for resistive load, right, it resembles, when RL is greater than R naught, it resembles open circuit line. Just now only we studied what is the nature of open circuit line, right? So open circuit line means V max and I minimum occurs at load. Yes or no? Open circuit voltage is maximum. Fine. So and another thing is V max is smaller, very less, and I minimum is not equal to 0. In open circuit load, it is exactly 0. Here, I minimum is not 0. Since I minimum is not 0, V and I will give power which is not equal to 0. Right? Because P is equal to V max into I minimum at load. Right? What is the power at load? In power, V max at load, V is V max, I is I minimum. I minimum is not equal to 0. I minimum is equal to 0 in pure open circuit load. But here it is RL is not infinity, it is less than infinity. It is a resistive load. Okay, then another thing we have to know is, right, so and moreover reflection coefficient is positive. Next, okay, suppose if RL load resistance is less than R naught, right? So it will become, it is appearing resembles a short circuit line. It resembles short circuit line. So what happens? RL is less than R0. So RL load must be less than R0. Maximum is characteristic impedance. So RL lies between 0 and R0. So since it is short circuit line, IB minimum, R, I and I max occurs at load. Okay. So it is resembling short circuit line. Okay, this is the way. So in dissipation lines, this line, what will happen if the load is open circuited, short circuited, and if the load is resistive, right? So these are all the things we must remember. Okay. Next point we must know is what you call skin depth. Skin depth is given by delta, that is equal to 1 by root of pi f mu sigma. I have put one complete video for skin depth. Please refer the detailed analysis of skin depth. Right? So pi f is frequency, mu is permeability, sigma is conductivity. Okay. So these things we must. Next one is phase velocity. Right? So velocity, it is a velocity at which sinusoidal signal, right? It is a velocity at which sinusoidal signal travel down in lossless transmission line, right? So that is known as phase velocity, that is given by V is equal to 1 by 2 times. Fine. So this is another thing we must remember. Okay. Next we learn about impedance matching. Here we have three techniques. Impedance matching in transmission line. Right? So one is quarter wave transformer. Second one is stub matching. And by using a Smith chart, we can try to match impedance. Right? Okay. First we see what is the important thing we must know about quarter wave transformer. Fine? Okay. Quarter wave transformer QWT. Right? Characteristics impedance is given by Z0 is equal to Z load impedance into input impedance. Based on this equation, so many problems have been asked, so this is very important. And quarter wave transformer is used as impedance inverter. Right? So that is another important point we must know about quarter wave transformer. Right? So it is used to couple transmission line to a resistive load. Such as what is the resistive load, for example? Antenna. So these are all the points we must know about what do you call quarter wave transformer. Fine. This equation and impedance inverter is very, very important concept. Next, what do you call next one is stub matching. Stub matching. Right. So stub is nothing but a small transmission line. Right. So what stub matching can be used for impedance matching. So here we have two techniques. One is single stub matching. Another one is double stub matching. Right? So double stub matching. Fine. So in single stub matching, what are the things we have to remember? It requires what do you call both length and location. This is very, very important point. location of stub to be altered for matching. That is the first thing we must load and length and location of the stub to be altered for single stub matching. Second point we have to remember is what we call. Second thing is stub should be placed at definite place. Stub must be stub should be placed at definite place, right? So that is the next point. And the third one is it doesn't involve lumped elements, right? Okay, so it doesn't involve lumped elements. That is the third point. Fine. So everything is distributed element like a transmission line. And fourth one is it can be fabricated as part of transmission line. It can be fabricated as part of transmission line. Okay, so these are all the things you must know about single stub matching. But what are the disadvantages of single stub matching? It requires variable length. It requires variable length of line, where it requires variable length of line between load and stub. Right? Second one, change in Zn result. If load impedance is changed, change in ZL results in change in length and location of stub. Results in change in length and location of stub. Right? So these are all the main disadvantages of single stub matching. Okay, right. In double stub matching, only length must be altered, right? Only length must be altered. Whereas in single stub, both the length and location must be altered, right? Okay, and it can be placed anywhere. It can be placed arbitrarily, right? So that is the second thing we must know. Then that is an important point, right? So these are all the things we must know. Then we have to know about what you call short circuit stub and open circuit stub. Short circuit stub, what are the things we have to know about circuit stub is, short circuit stub is widely preferred compared to open circuit stub, right? Because right, preferred over open circuit stub. Because in open circuit stub, what will happen is radiation will take place. Radiation from one end, right? Radiation will occur at one end, right? So radiation will occur at one end in open circuit stub, right? So that is another one important point we have to know, right? So next thing, what are the things we have to know about is we should learn about Smith chart. So Smith chart. What are the important points to be noted in Smith chart? The first thing is it is a polar plot. It is a polar plot, right? And which plots gamma value, that is reflection coefficient, with respect to normalized Z0, normalized characteristics impedance. Second thing we must know about Smith chart is it is frequency domain plot, right? So this is another thing we must know. Okay, by using Smith chart, what we can do, we can calculate we should calculate. What are the things we can calculate? Gamma, VSW, or for normalized Z. Okay, so what are the components of Smith chart? It comprises, what are the things? It comprises constant R and constant X circuits. Fine. So these things we have to know. Next thing is in Smith chart, right? The upper part refers, upper part or upper of refers positive reactance or inductive reactance, right? And the lower of refers or lower part refers negative reactance or capacitive reactance. This is another important thing we must know. And one more point we must know about Smith chart is to get to get an impedance, we know impedance we can find in Smith chart. To get an impedance chart from impedance chart, what we should do is rotate Smith chart by 180 degree, right? So this is the thing we must know, right? So I think these are all the important points you must know about what you call transmission lines. I hope if you have any doubt, please ask me in comment section. I will clarify. Thank you.
Hi friends, in this video let us talk about antenna and wave propagation that is useful for any exam, right? Such as a TRB, TAB and a GATE. It's just a review, not full theory. So whatever the concepts which are all important for examination point of view, that only we will deal, right? Okay, so the first one is we must know what is antenna. Right, so antenna is a radiator. It is a radiator. What it will do? It launches EM wave into space. It launches EM wave, electromagnetic wave into space. That process is called radiation. Then what it will do? Right? Antenna couples EM energy from transmitter to free space. So that is one of the main function of antenna, and also from free space to receiver. The function of antenna, and it is a bidirectional device. Antenna is a bidirectional device. Fine. Okay. So what is the meaning? Power can flow through the antenna in both the directions. So from transmitter, same antenna can act as a transmitting antenna and a receiving antenna. One antenna can act as both transmitting antenna and receiving antenna. That's why it is called a bidirectional device, right? So this is the first important thing. Okay. Then to have a radiation, so antenna is a radiating device. We must know when radiation will take place. To have radiation, we should have two things. One is we should have time varying current. Time varying current means a current which is varying with respect to time. It is nothing but our alternating current AC, right? So second one is spatial imbalance. That is spatial imbalance. Spatial imbalance, it implies that, so we know that antenna is a conductor here current flows in this direction, here current flows in this direction, right? So this gap d, that must be far less than wavelength of the wave transmitter. So these two conditions should be satisfied by the antenna. Then when radiation will be dominant? Radiation is dominant at high frequency. Okay, so it is very important, right? Weaker at a low frequency, and radiation is zero when DC. That is, DC means F is equal to 0. Frequency is 0. So when frequency increases, what will happen? You see the radiation increase. So F increases, radiation will increase. Okay. This is the next thing we have to remember. Next. So these are all the fundamental basic theory. We should know about what is the definition of antenna and all, right? So next we have to see what are the important characteristics of antenna radiation pattern, right? So radiation pattern. What is radiation pattern? Radiation pattern is nothing but pictorial representation of radiation of antenna. Pictorial representation of radiation. We cannot see radiation, but we have to feel it. So for that we give some shape that is called radiation pattern. Pictorial representation of radiation of antenna. This is called radiation pattern. Let's take one antenna with radiation pattern like this, right? So here you see these are all the things we have. So let us see, right? So here you see the maximum radiation in this direction. So this is called main beam, right? So this is what intended direction. These are all unwanted radiation. So this is called side beam, right? So this is main beam, this is side beam, you can see, right? So the gap between the beams, this is called null. Here you see this one is null, here also null, right? Here you can see major beam, here you can see minor beam. Fine. So this is, so minor beam indicates unwanted radiation. Actually the radiation should be in this direction. So minor beam indicates unwanted radiation, right? So you see this, we normalize the radiation and the maximum value of radiation, let us assume it is 1. So if it is reduced by 1 by root 2, that is 0.707 on both sides, the region covered by this is called, this gap, this is called off power beamwidth. So at this point the power is reduced by half. So that's why it is called off power beamwidth, right? So you see this is one null, this is other null, right? So the gap between these two is known as beamwidth between first null. Beamwidth between first null. Null means the region where there is no radiation. Region where there is no radiation. The region is called null. Right? So these are all the things we have to know. Right? So next we have to know what is directional antenna. Directional antenna is when it is high directional. Or highly, this is highly directional or has high directivity. We will see what is directivity later. Right? So high directivity. That means if antenna radiates in particular direction more, then that antenna is called directional antenna. So here you see this is the radiation pattern of one particular antenna. You see this antenna radiates in this direction. So all the radiation are converged in this direction. It is highly directional. Whereas you take this antenna with radiation pattern equally distributed in all directions, this is low directional because we cannot say which direction the radiation is maximum. So it is low directional. This is a radiation pattern of low directional antenna. Okay. So the best example is our laser light. If you consider laser light as antenna, it is highly directional. The light is focused more. Right? If you take our bulb as antenna, it is radiating light in all the directions. So it is poor directional or low directional antenna. Our bulb is a best example for low directional antenna. Fine. So next what we have to know is radiation pattern. Just now we have studied about radiation pattern. We are having two types of radiation pattern. One radiation pattern is E pattern. E pattern is drawn between magnitude of electric field versus theta or constant pi. It is called E pattern or vertical pattern. We have two types of radiation pattern. So one is E pattern and another one is H pattern. H pattern is also called horizontal pattern. We call H pattern as horizontal pattern. It is drawn between En versus phi for theta is equal to pi by 2. Right? So antenna is radiating in spherical nature. So that's why we are using spherical coordinate system r theta phi. So radiation is r direction. So theta and phi are varying. Here for constant phi, if you draw a radiation between E and theta, that is called E pattern. The H pattern is drawn between En versus n is normalized. So En versus pi. This is called H pattern. Okay. So these are all the two types of pattern available. Okay. Next one, we should know the radiation character. Another important thing we have to know about is radiation intensity. Radiation intensity Ri, it is given by the symbol Ri is equal to power per unit solid angle. Power by unit solid angle, where I write power as watts, solid angle as a steradian. Okay, so the unit of solid angle is steradian. Okay, so radiation intensity is given by watts per steradian. So the symbol of radiation intensity is U of theta pi. That is given by power. Power is theta phi. Solid angle is d omega. So solid angle I can write as dA area by r square, distance, right? So dA by r square. D omega is dA by r square, right? So this is radiation pattern. Okay, so U theta phi in terms of this is in terms of power. Radiation intensity in terms of power. Radiation intensity in terms of electric field is E theta phi squared by eta into r square. Right? So this is radiation pattern in terms of power, radiation pattern in terms of electric field. So I can write U theta phi. This one is P average, that we know, average power into r squared. Right? So in magnitude wise, average radiation intensity is given by sum divided by total. P radiation by 4 pi. Total solid angle is 4 pi. Like radian we say 2 pi, no? So total angle, solid angle is 4 pi. So U average is sum total radiation divided by total. So that is called radiation pattern. U average radiation intensity. Right, so U average I can write as, so this is sum, so integral P theta phi d omega divided by total. Fine. So this is the first thing we have to know about radiation parameter. Another important parameter is directivity. Directivity I can write as D is equal to maximum radiation intensity from antenna to the average radiation intensity from antenna. Right? So I told what is directivity? It is how much the antenna is directional. So for omnidirectional antenna, the directivity is 1, the least value. What is omnidirectional antenna? The antenna which radiates in all directions. For that directivity it is 1. So this is called, see the radiation pattern. This radiation pattern has directivity of 1. It is radiating in all directions. So it is having least directivity. So that is the first thing. Okay, directivity indicates how much antenna is directional. So directivity is given by Umax divided by maximum radiation intensity divided by average radiation intensity. Next one, so I can write directivity in terms of what is the thing? So it is for in terms of half power beamwidth is theta hp by hp, right? In degree. So in radian, 4 pi divided by theta hp by hp radians, right? So these are all the properties of directivity. Then we must know about directive gain. What is directive gain? Directive gain GD. GD theta phi is indicated by radiation intensity in a given direction, theta and phi, divided by average radiation intensity. Okay, so this one I can write as GD I can write as directive gain is given by what do you call the average radiation divided by average power divided by radiated power multiplied by 4 pi r squared, right? So that is called uh, directive gain. So P average, from this what we understand is P average is equal to GD by 4 pi r squared into P radiation. Right? So that is one important relationship between G and directivity. Directive gain is equal to eta into D. Eta is efficiency. Efficiency of an antenna. Right? So next one, power gain. Power gain of the antenna is given by GP theta phi. Power gain is given by 4 pi u theta phi divided by input power. Right? So u theta phi is radiation intensity. Right? So this one we must know. Next one, efficiency of an antenna. Efficiency of an antenna is very important concept. So eta is given by R radiation resistance divided by radiation resistance plus loss resistance. This is called eta, efficiency. Eta I can write as power gain divided by directive gain. So power radiated divided by incident. So these are some other formulas for directive gain. Next one, effective aperture. Effective aperture is the receiver characteristics of antenna. So this is the only parameter which talks about receiver. It's the only receiver parameter. Other parameters are applicable for both transmitter and receiving antenna. Effective aperture is the receiving parameter. So it is indicating power capturing capacity of antenna. Power capturing capacity of an antenna. That you call as effective aperture. So effective aperture is given by the symbol AE. AE is lambda squared 4 pi into D. The other name for effective aperture is effective area. Right, so effective area is given by power received divided by power density. Power received by power density. So that is another important thing. So AE effective aperture I can write as in terms of transmitted power P transmitted 4 pi r squared into, sorry, this is power received. Power received I can write as power received is equal to P transmitted by 4 pi r squared into AE. Right? So for 4 pi r squared area, sphere, surface area of the sphere, this much power is transmitted means for AE how much power is received. So that is the thing we are talking about this one. Next thing we have to know is this transmission equation. This transmission equation is a very important equation. What it is telling is it is relating received power to transmitted power. So power received by the receiving antenna is power transmitted, gain of the transmitting antenna, gain of the receiving antenna, lambda by 4 pi r square. R is the distance between transmitting antenna and the receiving antenna. Distance between TX and RX antenna. That is called the phase transmission equation. Okay, so some important basic antenna we have to. What is the thing is? First antenna it's HCN dipole antenna. Right, so HCN dipole antenna. Right, so this is a small current carrying conductor. It is a small current carrying conductor. It is nothing but our wire, right? So small current carrying conductor. So it has, what are the components it has? It has HR component 0, H theta component 0, H phi component not equal to 0. Third one, it has ER component not equal to 0, E theta component not equal to 0, E phi component equal to 0. Right? So these are all the things we must know. The next one, right? So we are having some fields are here. Here 1 by r cube. In this antenariation, we have 1 by r cube, that is called electrostatic field. 1 by r cube is called electrostatic field. 1 by r square inductive field. 1 by r radiation field. Right, so these are all the things we must know. Then next point is, these are all things we must know about HCN dipole antenna. Fifth point is near field. A field nearer to antenna is called near field, which is given by if beta r is far less than 1, r is the distance between antenna and field point. Distance between antenna and field point. Right, so beta r is less than 1, it is called near field. Far field is beta r is greater than 1. Beta r is greater than 1, that is called far field. Right, otherwise we can say beta r, we can say that r is less than lambda by 6. Here r is far greater than lambda by 6. Okay, so the boundary between near field and far field is given by boundary between near field and far field is given by what do you call, which is equal to 2d squared by lambda. Right, here beta is nothing but phase shift, right? So 2d squared by lambda, d is the largest dimension of antenna. Right? Then the radiation distance, this is a very important point. Right? So power radiated by HCN dipole antenna is 40 pi squared I naught squared PL by lambda whole square. Similarly, radiation distance of Hertzian dipole antenna is 80 pi square dl by lambda square. dl is antenna length, lambda is wavelength of the antenna, and wavelength of the wave propagated by antenna, and I0 is the current. Right, so for Hertzian dipole antenna, D directivity is 1.5, right? Beam width 190 degree, half power beam width 90 degree, right? So these are all the things you must know about Hertzian dipole antenna. Next one is half-wave dipole antenna, lambda by 2. Half-wave dipole antenna. So for half-wave dipole antenna, we must know radiation resistance is equal to 73 ohm and directivity is 1.64, right? Total input impedance is 73 plus J 42.5 ohm. For L is equal to lambda by 2. What is mean by lambda by 2? The length of the antenna is lambda by 2. So that's why it's called half-wave dipole antenna. Right. Next one is we go to folded dipole antenna. For folded dipole antenna, one point is very important. What is that is Zn, input impedance. Input impedance is n square into 33, where n is number of conductors. Okay, so these are all things. Then regarding radiation pattern, so for half-wave dipole antenna, the radiation pattern will be like this. This is the radiation pattern of half-wave dipole antenna. This is vertical pattern or E pattern, right? So here antenna is assumed to be placed like this. So here no radiation. So Hertzian dipole antenna won't radiate along the direction of antenna, it will radiate perpendicular to the antenna. This is H pattern or E pattern or vertical pattern. What about H pattern? This is H pattern of half-wave dipole antenna. Fine. So this is H pattern. So this one you must know. Okay, the radiation pattern. And next we have to know about antenna array. So why we are going for antenna array? To increase the gain and radiation character. To increase gain and directivity, we are going for antenna array. Antenna array is group of antenna. So here we have two array. One is broadside array. Second one is end fire array. Right. So in broadside array, maximum radiation occurs perpendicular to the direction of array axis. Here it is along the array axis, end fire array, right? So second one for broadside array, total phase shift is 0, right? So it is radiating perpendicular that angle radiation direction. Then progressive phase shift is 0. For here, total phase shift is 0, theta is 0 degree along direction, so 0 degree or 180 degree. Progressive phase shift is plus or minus beta d. Okay, so then beam width between first null for broadside array is equal to 2 lambda by nd. N is number of element in array. D is distance between two element. Lambda is a wavelength. Here, beam between first null for end fire array is 2 into root of 2 lambda by nd. Okay, so this is another important thing we have to know. So for a broadside array, directivity is 2 into L by lambda. For end fire array, directivity is 4 into L by lambda. Right, and antenna effective noise temperature. Effective noise temperature T is equal to T naught temperature at room temperature Fn noise figure minus 1, right? So this is effective noise temperature. So these are some overall picture we have to study by taking all these things into account, right? So without, again, in addition to this, we may ask types of question from UHF and VHF antenna, so that we have to read. So regarding wave propagation, what is the thing we have to know? In wave propagation, we have to know what is critical frequency. That formula is very, very important. Critical frequency Fc is given by 9 root N, where N is the electron density. Then we should know about maximum usable frequency, that is given by Fc secant theta I. So that is what Fc is critical frequency, right? So this one is another important point. Then refractive index when wave propagates through a medium. Refractive index n, small n is equal to root of 1 minus 81 n max divided by f square. So this is another important point, right? So n is the electron density, right? So n is the refractive index is this one. Okay. Then another thing we should know about is skip distance. Not okay. Skip distance is given by ds is equal to 2h and theta c. Theta is critical angle. Okay, then radio horizon. Radio horizon distance between transmission and the receiving antenna is given by what we call the kilometer 4.12 ht in meter plus root of hr in meter. ht is height of the transmitting antenna, hr is height of the receiving antenna. Right? So these are all the things we must know whenever we study about antenna. So next we learn about waveguides, right? Important points of waveguides. So what is waveguides? Waveguides also they guide electromagnetic energy from one point to another. Right? So like transmission line, waveguide also guides electromagnetic energy from one point to another. So it is a special case of transmission line. Right? So transmission line is a low pass filter, whereas waveguide is a high pass filter. So they must be used only at a high frequency, that is above cutoff frequency. So that's why we are finding cutoff frequency is a important parameter in waveguide. So transmission line supports only TEM, right? So whereas waveguide supports any possible field configuration. Any possible is very, very important. Field configuration, right? Okay, so this is the thing we have to know. So who's dictating the structure of a waveguide? So we know waveguide has some structure. So the terms dictating structure of waveguide. Structure of waveguide is dictated by one, right? So operating frequency, F operating. Second one, the amount of power to be transferred. Amount of power to be transferred. So this is another parameter which decides the structure of waveguide. Third one, amount of losses. How much loss a waveguide can tolerate, right? So amount of losses that can be tolerated. So power, frequency, and loss. These are all the factors which decide which structure of waveguide we have to use, right? So next, so what are the important things we have to know? Let's see, right? So first one, so main concept that is asked in any TRB exam is rectangular waveguide RWG. For rectangular waveguide, the electric field along its direction is given by minus gamma by h square. Gamma is propagation constant. Dou E z divided by dou x minus j omega mu divided by epsilon square dou h z by dou y, right? Similarly, electric field along y direction is gamma by h square dou E z divided by dou y plus j omega mu by epsilon, sorry, not epsilon square, it is square. J omega mu by h square, j omega square, dou h z by dou x. So this was electric field. Similarly, for magnetic field, Hx along x direction, gamma by h square, dou hz by dou x plus j omega epsilon by h square, dou Ez divided by dou y. Similarly, Hy is equal to gamma by h square, dou hz divided by dou y minus j omega epsilon by h square dou Ez by dou x, right? So these are all things we must know. Then propagation constant of rectangular waveguide, gamma is given by omega m pi by a square plus n pi by b square minus omega squared mu epsilon. The unit is 1 by meter, right? So A cross B is dimension of waveguide, right? So A is a larger dimension. M and N are mode number. Fine. Next, phase constant beta. Beta is called phase constant, that is given by omega square mu epsilon minus m pi by a whole square minus n pi by b whole square. Next one, phase velocity, which is given by omega by beta. Next, wavelength, guided wavelength, 2 pi by beta. Beta is given by this equation. So the unit of beta is radian per meter. Okay, fine. Next one, guided wavelength. Guided wavelength lambda g is given by lambda naught divided by root of 1 minus fc by f whole square, or lambda naught root of 1 minus lambda by lambda c whole square. So this is free space wavelength. Lambda naught is free space wavelength. So this is another important parameter. Then phase velocity Vp is given by V naught root of 1 minus lambda by lambda c whole square. That is equal to V naught root of 1 minus fc by f whole square. V naught is velocity in free space, which is 3 into 10 power 8. This is phase velocity. Next one, this is phase velocity. Right, next one, group velocity. Vg is equal to V naught divided by V naught into 1 minus lambda by lambda c square. That is equal to V naught 1 minus fc by f whole square. This is group velocity. So we can write another formula for phase velocity, that is given by lambda g by lambda into c. 3 in 10 power 8. C is 3 in 10 power 8. Group velocity is lambda by lambda g into C. So when you multiply both Vp into Vg, everything will cancel. So we get C squared. Right? So these are all the things we must know. When dominating mode, so dominating mode for rectangular waveguide. Dominating mode for rectangular waveguide is given by TE10. What is dominating mode? Mode with the least cutoff frequency or maximum cutoff wavelength. That is called a dominating mode. So TE10 is that category. So for this cutoff frequency is V0 by 2A. Lambda C is equal to C by V. So that is 2A. Right? So this one you can use it for problem solving. Okay. So these are all the things we must know about waveguide for TRB exam. I hope the video is very helpful for you. If you need any clarification or any material, ask in comment section. Let me try to fulfill your wish. Thank you.